We will wait for 1 or 2 minutes, then we will start the session. Okay, so we will start the session today. So, good evening everyone. Welcome to the series on exploring nonlinear dynamics from basics to applications. So, till the last lecture, we have seen basics of nonlinear dynamics and what are the different applications in engineering and physics that we saw in the last class. So, in this class, we will try to see the application of nonlinear dynamic concepts. Specifically, we will focusing on the area of aerospace engineering. So we will see how these nonlinear dynamic concepts which we have learned till now can be used into these aerospace engineering things, and see how people have used them to discover really great things in this area. So as usual, these are the books which are referred, and this time you can use thermoacoustic instability, a complex systems perspective, in which most of the things have been you can measure, and you can use the YouTube videos that are mentioned here for references. Yeah, so we will start our session 12. So I will start by telling a story here. So if you remember, I will just show a video over here. So this is a video by John F. Kennedy, the 16th President of United States, and in one of his sessions he mentions this ball. Yeah, so okay. Yeah, so you have seen this video. So this was, so what I am showing you, so this was in 1960s, when 1950s nearly, where John F. Kennedy was giving his speech in Rice University, and this was the conditions when the space race was going on between Soviet Union and the USA, and Soviet Union was sending the Sputnik 1 and Sputnik 2 missiles and to the space, and they were a little ahead. And so in that time, John F. Kennedy publishes in the Rice University that, and he says, and it's So he mentions this famous quote of it where he says, we choose to go to moon. So this was the beginning of a new era where people wanted new very high level of sophisticated engineering techniques and all were coming into play, where to meet a requirement of a nation and basically it was near the Cold War time and space race was at its peak there. And with that said, so that triggered into developing a very high massive rockets which are built for these missions. And you may know these are called Apollo mission, and Saturn rockets have been built for this. And the Saturn rockets are so massive and they are one of the biggest rockets that have been built in the mankind history. And so here I have shown a part of that, and you can see at the bottom you have 5 different nozzle exits being shown here. So these are the 5 nozzles called the F1 engines, which are used to push the whole rocket in the towards its desired path. And so Sunny Moray was a project manager of this particular mission, and he found that, and he says in one of his, so that also we will just play here. So before I talk about that, so he says during this successful mission where they tried to go to moon, the biggest problem they faced and you can see the NASA and its blasts on the test stand. So this is when NASA test fires its F1 engine rocket engines for these Apollo missions, and within the test stand itself the engines were blowing apart. They were, and they saw the problem which created this was called combustion instability. We will discuss it what it is. So in order to explain what combustion instability in an aerospace engineering is, so he tells a small example where he shows that example, visualize a candle in a room and it flickers from side to side and other side. So this flipping back and forth, it can take nearly 5 to 6 times but in an F1 engine, where in an F1 engine this flipping happens nearly 2000 times in a second. So this is as shown here, this engine, and it eventually destroys the engine. So that was the main. So the F1 engine rocket engines, when they were building up, so they massive, and the Apollo mission was a very serious mission at that time, and people were trying to work very hard to solve this problem called combustion instability. And so this is the one of the stories which I wanted to start with. So this kind of instabilities were very crucial for a mission like Apollo mission. These were very critical, and people wanted to solve this kind of very high it's very complex system, because we will discuss how it is complex and all. So how nonlinear dynamics comes into play here is, so we saw how a dynamical system or a nonlinear systems, how they can behave to, what are the different behaviors dynamics they can show. So we will look into how this problem of combustion instability in a rocket engine, and as you saw, combustion instability is very catastrophic. It results in very high amplitude oscillations in a system, and eventually it results in breaking of the engines and even breaking of the mission failures and all these things. It was a path breaker or path blocker for the Apollo mission. And so with this we want to see how, but there is, this can be avoided. Why? Because energy conversion through combustion is what you need for these aero engines and gas turbine based power plant engines. Combustion is needed for them to drive these engines, so you can't avoid combustion in there. But and also due to the stringent norms on the NOx emissions, so the emissions that the rockets or gas turbine engines produces, there are stringent norms on them, and the engines are preferred to run under such lean conditions or under low fuels values, such so that they don't produce such amount of NOx emissions. And the problem comes here is when you are working at very lean conditions. These are the favorable conditions for the combustion instability to happen. And in short, combustion instability means in your closed confined chamber you have a acoustics being set up inside your system. Acoustics in the sense you have a sound due to the flow or due to any of the process, you have pressure oscillations or acoustics being created in your system. And in a closed chamber, when these acoustics are get energy from the system, and the acoustics get energy from the combustion, which drives the system to very high amplitude oscillations. Say you have a acoustics being built up in your system, and eventually when your heat source is present in your system, and if the heat source is able to provide the energy at the correct time or at the correct in phase with the oscillations, then they will result in such kind of high amplitude oscillations. And these high amplitude oscillations you have seen in the video, these will result in very high amplitude oscillations and eventually will break down the structures or engines in the rockets and gas turbine engines. Now here in the left I am showing a sample pressure time series of CFD modeling. This looks pretty good, that's why I just, it's not an experimental result but it's a CFD modeling result. And you can see that initially the system remains at very low amplitude and quiet conditions, and slowly it gradually increases and it goes to this high amplitude oscillations. And if you remember from the nonlinear dynamics which we have learned till now, this region where you have a periodic oscillation being set up, this in by characterization this is usually called a limit cycle oscillations, because they have a isolated closed orbit for them. No other closed orbits are present around it, only the system moves towards these kind of these closed orbits. So they are called limit cycle oscillations, which we have learned from the nonlinear dynamics. And transition from this kind of very low amplitude to this very high amplitude oscillations in a real system, this takes within a fraction of seconds. These all things within seconds, these things happens, and it's very fast, and you need to be very careful for when these kind of high amplitude oscillations happens in the system. So here I have shown a video on the top, the video of the F1 engine getting exploded during the test, and you can see the system as engine was started, the system blew and it blew apart with this due to this catastrophic or due to this undesired state called thermoacoustic instability, which is nothing but this high limit cycle oscillations which we are seeing here. And now one more example which we are showing here is the collapse of a Tacoma bridge, where the bridge was initially at a state of stable state where you can see this linear region, and after a particular way it was seen that the oscillations were building up and it showed a very high amplitude oscillations, which eventually resulted in this blockage of this bridge. And so this is also an example of transition from a state to an undesirable state. And these kind of transitions from one particular state to another, they are usually referred to as critical transitions. And understanding the complex dynamics in such systems is challenging, because due to multiple subsystems, they interact with each other and they evolve to produce a global change. And these multiple interactions between these subsystems, they are completely non-linear, and understanding them is very challenging. Hence people use different tools to study these kind of complex systems, and nonlinear dynamics is one among them, which we tried to learn in some basic sense in this previous sessions. And so in order to study that, so in IIT Madras we have a lab called the Center for Excellence for Studying Critical Transitions in Center of Excellence for Studying Critical Transitions in Complex Systems. So this lab in IIT Madras in Aerospace Engineering. And so here we have different lab scale combustors to study this thermoacoustic instability and how you can mitigate it, what are the precursors for before these systems goes to thermoacoustic instability, and different systems and mitigating this thermoacoustic instability, suppressing them, passive control methods. All these are our different areas which our current group works on. And so I just showed different equipments, major equipments which we have, setups, and the first one is called a Rike tube setup. So it's a laminar thermoacoustic system. So by laminar we mean the flow. So here you can see there is an air compressor being provided, and this air compressor goes on through this mass flow controller, and it goes on to a decoupler where any inherent fluctuations in the system is removed by this decoupler, where it makes the flow settle down and the flow passes on through this duct. Now we have electrical leads being provided within this duct, and we have a pressure transducer being provided in this Rike tube to measure the acoustic fluctuations inside this tube, and you have a flow being passing on through this decoupler through the Rike tube towards this. And so in order to test the decay rate within this tube, we provide something called loudspeakers to test this, how if you give any acoustic pulse to the system, how with what rate the acoustics will decay. In order to measure them, we use loudspeakers, and we have thermocouple ports to measure the mesh temperatures and air temperatures. Now the second picture here shows an turbulent combustor, which is a bluff body stabilized turbulent combustor. So in combustors you need to hold the flame properly, else to reignite the fuel and air will be coming back to back. So you need to keep on igniting the fuel and air mixture. So in order to do that, you need certain flame stabilizers, and the one which is used here is, we use different stabilizers. So we use bluff body stabilized combustion, and we have a swirl stabilized combustor also. So we use bluff body stabilized combustor over here, and so here also you have the fuel valve being provided here, and you have air being coming through this, and they will come mixed together, and they will be coming into this plenum chamber, and they will be passing on through this tube towards into this combustion chamber. So this is our combustion chamber provided here, and you have an optical access over to do the PIV and camera imaging and all techniques. So this is the camera used to take the images of this flame and all the flow dynamics over here. And so in a turbulent combustor, you can see it's way more challenging, and more challenges are upcoming there. Now this mimics a gas turbine engine which are used in airplanes. Now we have another setup called the swirl stabilized combustor. It's called an annular combustor, not a swirl stabilized combustor. It's a swirl stabilized annular combustor because we have, so these are the 16 flames. Here you had only one flame. Here we have 16 flames in these tubes, and each of them have a swirler attached on this top to mix the air and fuel mixture properly. And this is the mimic of helicopter engines, and so you have different fuel lines being provided in this duct, and which eventually comes to this plenum chamber, and it gets uniformly distributed towards each of the 16 burners, and they get ignited, and we study this occurrence of this thermoacoustic instability in these systems. And we have another setup called turbulent combustor with preheater. So as you have seen in the top, we have a bluff body stabilized combustor, but now in order to be more near to the practical engines, we need to preheat the air which comes in. So we have a preheater setup shown here. So we preheat the air as it comes through this. We heat this air up here, and then we provide this, and then we do the secondary combustion over here. And when we do this combustion over here, we can see the flow being passing over, and we take the optical imaging and PAV and all. So we try to study this during the thermoacoustic instability phase and during the transition from normal operation to the thermoacoustic instability case. So that's the major work we carry out. And so as I told, in the laminar thermoacoustic system called the horizontal Rayke tube, we have a mesh which is being positioned at a particular location, and we heat this mesh using an electrical supply, DC power supply, and we have a pressure sensor mounted on this tube to measure the acoustic pressure fluctuations that are present in the system. And as I told, we have a airflow coming through, and decoupler decouples it. So now, what from a nonlinear dynamics perspective, what is useful here is this kind of oscillations. So in a system like Rayke tube, we see that when your power, or this power means the voltage and the current that is supplied towards this mesh to heat the mesh, when it is at very low values, you can see that the RMS of the acoustic pressure fluctuations. So it's like you take the root mean square of the total pressure time series that you are getting here. If you take the value, so this is basically what we call the bifurcation plot, which we have seen for different logistic map and all. We have seen the bifurcation maps. We have seen for different transitions also. So we have seen for pitchfork bifurcation. We have seen for transcritical saddle node bifurcations. We have seen the how bifurcation plots needs to be plotted. So our x-axis needs to be the control parameter, and here the control parameter is the power that is supplied to the mesh. And you can see initially when the heater power supplied to the mesh, when it is at low values, the system remains at very low amplitude of pressure oscillations, and as you increase slowly the heater power, we see that at a particular point called mu here, the system jumps to very high amplitude oscillations. These high amplitude oscillations are developed due to the positive feedback between the acoustics that are present in the system and the heat release rate from the mesh that is being shown here. Here we don't have a flame. Here we have only the heater mesh, a compact heat release zone we have. So this manifestation of sudden rise in the RMS is nothing but is an example of Andro-Hoff bifurcation, which is popularly known as Hoff bifurcation. And this kind of sudden jumps, and when you return back seeing a, so it's called subcritical Hoff bifurcation, which we have learned. So we will discuss it in the next slide. So this is a review paper which was published, in which you can get all the details on this Rayke tube setup. So if you look carefully, so when your airflow rate is at say at low values of say at 60 SLPM, it has been shown that the filled triangles here, if you observe, this is the forward path where you are slowly increasing the heater power, and if you observe, we can see that the system slowly gradually increases towards the high amplitude oscillations. And when you return back, when you are decreasing the voltage after you reach here, we see that the system still follows this same path and it reverts back in the same path. So this is an example of supercritical Hoff bifurcation, where, so we say it as a Hoff bifurcation since from our definitions which we have learned, Hoff bifurcation happens when your system transits from a stable point, from a steady point to a limit cycle oscillations. When such things are happening, we say it's as a supercritical Hoff bifurcation. And similarly, when your values of flow rate are higher, say at 100 SLPM, you will see, and you can observe from here, as the dotted filled triangles are the forward path, we can see that as we progress from increase the heater power, this value slowly increase, and at a particular point called the Hoff point here, the system abruptly jumps to very high amplitude oscillations, and you can see here. Now when you revert the parameter back, you can see that the system will not come back at that particular point, rather it follows a further lower values till the further lower values it comes back, and at the point F called the fold point of the system comes back to the low amplitude oscillations. So this is an example of subcritical half bifurcation, where you have a steady state and you generally go to limit cycle oscillations due to the sudden disappearance of the unstable limit cycle. Then when you are reverting back the parameter slowly, you will see that in order to cross this unstable limit cycle thing, you need to come back till very low values, then you will eventually come down to a steady state operation. So this is how in a physical system you can observe both supercritical and subcritical half bifurcations, and this is the region between them is what we call referred as hysteresis region or bistable region. And so if you look into this 3D plot over here, and here they have showed for different values of mass flow rate of fuel for an equivalent normalized ratio of the heater power. We can see that when your values are very low, when your air flow rates are very low, you can observe the system smoothly increases to low amplitude oscillations, whereas when you increase after a particular value called this 60 SLPM, if you are seeing, you will observe that system even slowly comes in the steady state and it abruptly jumps to high amplitude oscillation and grows up. This will not keep on growing after infinitely, because in real experiments you have viscous forces, boundary effects and all these resistances which cause the amplitude from increasing to infinitely. So we have certain damping forces which cause your dampings to be settled down, and if you move to very further higher values of 100 SLPM, you can see that the jump is very high from the lower value to high amplitude oscillations, and it goes up, and when it returns you can see this gray shaded region represents the bistable region over here. This is the bistable region over here. So that's the part of Ricke tube. And so in nonlinear dynamics what we learned and we used, so it's a practical example of supercritical and subcritical half bifurcation, and to see how your dynamics in the system is behaving, which nonlinear dynamics gave us a very good helping hand to see how to understand this mechanism which is happening over here. And the plots here, the bifurcation plots, are able to help us understand this. So nonlinear dynamics tool is pretty helpful for us to understand such complex dynamics. Now when you are going to the second engines, so these are the second engines called the combustors, called turbulent combustors. When compared to a laminar thermoacoustic system, as I have shown here you have a state of steady state, then you go to high amplitude oscillations. And contrast to this, when you are going with a turbulent combustor where you have very high Reynolds numbers, their system exhibits lot of turbulence and lot of strong vortices are being produced in this system, and you will not observe as we seen in a simple steady state and then going to high amplitude periodic oscillations. Instead we observe something like, initially you will observe very chaotic behavior from the system. This here shown is the, so here what I am showing, this is the so this is the region, this is the time series which you obtain for the initial states when your values are low. This region is called the combustion noise, we say, and a zoomed in version of the signal is shown here. So it's completely chaotic, it doesn't have any periodicity in it, and it's completely random. But we will just see how combustion noise is a deterministic chaos actually. And then if you see the next final state, that is the thermoacoustic instability state over here, you can see that this time series looks like this, and the expanded view, if you see, it's a periodic, clean periodic sinusoidal signal you can observe. So transitioning from this chaotic behavior to this kind of high amplitude oscillations, it is being shown that, it has been shown by Vineet Nair and Professor Sujit, that there is an intermediate state between this transition from combustion noise to thermoacoustic instability, where you will see intermediate periodic oscillations amidst aperiodic fluctuations being present in the system. And this state is what we call intermittency, where intermittency was reported, but in thermoacoustics this was reported first by them, and where you will see this kind of high amplitude periodic oscillations and you have sudden small amplitude aperiodic oscillations being present over here. So there is a transition from combustion noise intermittency to thermoacoustic instability in turbulent combustors. And studying such complex dynamics, when in a turbulent combustors you have all flame, flow, you have hydrodynamics, you have heat release, you have acoustics. So all these multiple subsystems, they interact at very high with very high order interactions, and studying them is very challenging. So nonlinear dynamics is one of the helping tools which we use to get more information out of this time series what we are having. And so as I said, if you look into the combustion noise, it is been proved that it is actually a deterministic chaos. So by chaos what we mean is, so a chaotic time series, if we look here, a chaotic time series has a self-similar structure with patterns that fill non-integer dimensions. So if you, for example, if you look, this is the DNA 3-layer being shown here by Pegg et al. At 1992 paper. If you see, you will see that if you zoom in this portion, you will observe the similar pattern being repeating further if you zoom. So under different scales you observe the similar structures being coming out of the system. So that's what we call the self-similarity in the structure, and chaotic time series has self-similar structures within them. And if you look into the pressure time series of a turbulent combustion, we can see that this is the pressure oscillations during the chaotic fluctuations in the system, and if you zoom in further, you will further observe the similar thing being shown here, and if you further zoom in, you still observe this similar chaotic time behavior being shown by the system over here. So this kind of self-similar structure is being shown by the system, and it is shown that combustion noise is actually a deterministic chaos. Whereas now when in a turbulent combustor, if you look into, turbulent flows which we see actually are self-similar, and like the images or signals whichever is there, they look the same statistically under increasing the magnification at different scales. So for example, I have shown here a galaxy. Like if you zoom in this galaxy further, you will observe further small similar pattern being shown by the system, and if you further zoom in, you will see the similar structure further down. So this shows a self-similar structure over here, and the chaotic time series, they show a self-similar behavior within them under different magnification scales. But in real data and all, you can't expect such clean self-similarity. It will be approximate until certain scales. That's the key to be noted. So up to certain scales, you can observe self-similarities, that to approximate self-similarities, not exact, in practical session. So in order to use this chaotic time series data and see how we can study this complex behavior that are shown in a combustor, in order to do that, we have different methods. So I have discussed autocorrelation and variance being discussed in the previous session. So this time I will discuss something called detrended fluctuation analysis, or which we use to study what we have referred there as Hurst exponent. It's a fractal based measure. So we have seen what are fractals in the course over this time, which have fractional dimension and which shows a self-similarity over different ranges of scalars. So if you are having such a kind of time series in your hand, you can use these kind of tools to get interpretations about the state of the system and all. So in order to do that, what we try to do here is, say here in the blue shown here, you can see the time series of the signal being shown. So here it is initially shown is for multifractal time series where you have different fractional dimensions for the system, not a single fractional dimension, but you have multiple fractional dimensions for this particular signal or shown here. And for a monofractal time series, you can see there will be only a single fractional dimension for the entire time series which are shown here. Whereas for a white noise, there will be lot number of frequencies that will be dominating over here in the white noise condition. Now, in order to do this detrended fluctuation analysis, or to do the what we call multifractal detrended fluctuation analysis, in order to do that, we need to convert our time series, that is this blue time series, into a random walk. So in order to convert this into a random walk, you just need to subtract your mean from them and keep on moving in windows over this thing, and you will observe this change. So what we need to do is, you need to take a window, you need to subtract the mean from it and do the cumulative sum of that. So once you do for a particular point, then you do a cumulative sum in the next point and keep on adding, and finally you will see this kind of the red color shown here. It's called the random walk time series that is shown here. And so for a multifractal, you will see there is an up and down trends going a lot of times, whereas for a monofractal you will see that the system grows in particular thing and then it comes down and remains there. For a noise, since I have told there are different frequencies being dominant, all frequencies are given equal importance in white noise conditions. So you will see that the red curve remains nearly approximately straight line over here. Now once you have converted your time series into a random walk, we try to divide the integrated combustion noise series, or the signal which we have, into different segments. So if you focus on the first time series over here, we have the random walk time series which is shown here. Now we try to detrend it into different segments. So here they are doing a linear detrending with m equal to 1 they are doing. So if you do that, you will see, and you try to fit a line for this particular section of the time series. So you will see these dotted lines are the fitted line for this particular sections, for each of these sections. Now if you try to do a quadratic detrending over the system, you can further see that the curved structures, we are able to capture more and more information in this. And for a cubic structure, you will see there is a little bit over fitting or being done over there, and still it captures this. So once you have a random walk time series, you then try to convert it into different segments and you detrend them locally. Once this step is being carried out, then the next step is to plot the RMS of this pressure these detrended values against the different segment sizes or different scales of the system in a log-log plot. The slope of this log-log plot between the RMS and the segment sizes is what we call the Hurst exponent, and Hurst exponent is related to the fractal dimension d of the system. So fractal Hurst is nothing but d minus 2. Fractal dimension is d is nothing but 2 minus Hurst exponent. Now if you observe here, for initial combustion noise case where you had a chaotic time series being shown here, you can see that the Hurst exponent for this particular thing remains nearly at 0.32, whereas for a monofractal time series where you had a single fractional dimension for this entire system, you see that the Hurst exponent lied nearly at 0.74, so it's way above 0.5. And if you observe for a white noise that is shown here, you can see the Hurst exponent is nearly at 0.49. So this 0.49 is our reference for when you are talking about Hurst exponents things. So with the Hurst exponent nearly at 0.5, we try to categorize the systems into two different cases. So for a normal white noise, we see the Hurst exponent is at 0.5 and signals are classified, and for a persistent signal the Hurst exponent lies between 0.5 and 1. So for a persistent signal, we mean is if you have a uptrend for an initial point, then there is a probability that the next segment will also have an uptrend. So that's what we call a persistent signal, and it will have a long-term memory. That's what we mean by that. So here for a persistent signal, for such signals, the Hurst exponent lies between 0.5 to 1. So this is what we have seen for the case of monofractal time series. You can see a trend being seen in this plot. So such signals are what we call as persistent signals, and Hurst exponent should be lying between 0.5 and 1 for such cases. Now for the case of white noise, as we seen in the previous case, the Hurst exponent lies nearly close to 0.5. And for the case where you have an anti-persistent signal, where your signal anti-persistent means if you have a positive trend upward, then it's probability that you will get a downward trend in the next segment is what anti-persistent signal means. And so when you are having a sinusoidal, you have a single scale being for this particular system. So when you are having a single scale for this sinusoidal signal, you will be seeing that the Hurst exponent lies between very close to 0.0 to 0.5. So this anti-persistence can be captured by the Hurst exponent by seeing the Hurst exponent values between 0 to 0.5. So now once we are able to classify these into different segments, now we will see how for the combustors, for a turbulent combustor, where we are seeing different states in a turbulent combustor, what are the Hurst exponent values for these systems. So when you are plotting the log plot against the standard deviation versus the time scale for this particular systems, for a white noise, as we have seen, the Hurst exponent values is nearly the slope is of nearly 0.5 plus or minus 0.005, pretty near to 0.5 here. And when you are having a combustion noise with a sweller as the this flame stabilizer, you will see that the values lie between nearly less than 0.5, exhibiting showing that it's having a anti-persistent behavior over there. And as you go for the bluff body also, you are seeing that the combustion noise values, they remain nearly at 0.238 values. And for a periodic data, when you are considering a periodic data over here, you will see that your Hurst exponent values are very close to 0. This indicating that the system has transited to a anti-persistent regime, and your Hurst exponent is able to capture this difference in the pressure time series or any signal. So, and people have tried to plot the broad spectrum for combustion noise and white noise and periodic data. So it is seen that when you are having a broad spectrum which are spread over different scales, you can observe that they are called, so this is for both sweller and bluff body, it is plotted here, and you will see that the broad spectrum is shown for the combustion noise conditions. When your system transits to periodic, you will have a single scale and it remains very close to the, so here it nears to the periodic oscillation state, that's why it is very close to 0. Here it is shown for the white noise condition, and it's nearly to 0.5, and this condition combustion noise region for bluff body and sweller is shown here. You can see a broad spectrum for this combustion noise regime you can observe, whereas for the periodic oscillation state, you will see that the system eventually condenses to a particular point in the spectrum. Now we saw that throughout this till now we have seen that there is combustion noise intermittency and instability in the system when the combustion chamber, and as you are transitioning from the combustion noise to thermoacoustic instability, we are seeing that our broad spectrum, that is this broad spectrum in the Hurst exponent, these are eventually condensing to a particular point in the system. So this eventually means that the system multifractality disappears when the system transits to at the onset of thermoacoustic instability. So that was the finding by Nair and Sujit in 2014, where they showed that the multifractality, so loss of multifractality is seen is what results in thermoacoustic instability, where it happens when you are moving from a stable operation to an unstable operation. So stable operation here is the combustion noise regime, and the unstable operation is the thermoacoustic instability state. And thermoacoustic instability state, and the combustion noise regime is also similar to the chaotic regime or the chaotic time series which we have seen there, and it transits to an ordered state. Ordered state means we are transiting to a periodic oscillation state over there. So there is a transition from chaos to order, or there is a emergence of order from chaos, and this can be captured using the Hurst exponent time series, Hurst exponent values in the system. Now we have seen that in between chaos and order we have intermittency being found by the system, demonstrated by the system, and we see that the intermittency, it presages the onset of thermoacoustic instability, and it's not a single state that is being shown by a single combustor or not. It is seen in most of the combustors that there is intermittency presages the onset of thermoacoustic instability. And here we have shown for a swirl stabilized combustor and a bluff body stabilized combustor. We can see that there are periodic oscillations amidst there is small periodic oscillations being present in the system, and these both signals, they demonstrate a intermittency like signals throughout the within the chamber. Now if you are trying to plot the trajectory between for this particular high amplitude periodic oscillation and the low amplitude chaotic behavior in the system, you will see that, so this phase space, if you are plotting, you will see that this is the pressure time series which you have, and if you take a delayed copy of it and you take a delayed copy to tau value, you will observe that for a periodic oscillation state the signal exhibits a clean circular cycle over here as shown here, whereas for a chaotic state you will observe that the system has a lot of chaotic behavior within this region, so it's completely random over here, whereas this black region shows the periodic oscillation state, so it exhibits a circular limit cycle oscillation like thing in the phase space trajectory. Now, so we saw that there is a transition from combustion noise to intermittency to thermoacoustic instability, and Hurst exponent, it smoothly, so if you see the first plot over here, it's plotted against Reynolds number versus the RMS of the pressure fluctuation, and if you look carefully we can see that at the very low, at lower values of Reynolds number, system initially grows slowly, and the blue shows the FFT peak of the system. The value slowly increases and it gradually increases towards this high amplitude oscillations when your Reynolds number reaches 2.2 and up into 10 power 4 and up. Now you are not seeing any before warning from the system because system is gradually increasing, and there are situations where you have the RMS being increasing steadily and it smoothly moves to the higher amplitude oscillations. Now if you observe for both these cases, so first one was for Searler and second one was for a bluff body stabilized combustion, and if you observe here, as your amplitude is increasing, your Hurst exponent, it decreases much before than your actual system goes to these kind of high amplitude oscillations, and you can see these Hurst exponent values, they come down before the system eventually goes to these kind of high amplitude oscillations, and it decreases and then eventually it comes to nearly zero values, indicating a periodic oscillation. So if you keep a threshold like 0.1 over here, you will get a warning saying that your system is eventually going to these kind of high amplitude oscillations. Similarly for a bluff body, if you observe, the Hurst exponent remains nearly to 0.25 over some time, and before the increase into high amplitude oscillation, the system decreases down to nearly to zero. So these kind of transition where you are not from the normal pressure time series when you are plotting, you are not able to get the system transition states. However, the Hurst exponent is able to show this. Hurst exponent, it is able to show well before the transition happens from a stable operation to an unstable operation. So this people use as an early warning signal, where they try to find these values pretty early before the system transits and get the warning of an impending tipping to thermoacoustic instability. And we can see from these two figures clearly that system, when it is here near to this region itself, you are getting a warning that you are going to some kind of thermoacoustic instability, so be aware. So you can say that you are getting some alarm over here, these two regions. Similarly, as we are approaching an impending instability, that's thermoacoustic instability in this case, we see that Hurst exponent approaches zero and a loss of multifractality is seen in the system. So if you take a Soule stabilized combustor or a bluff body stabilized combustion, in the combustion noise regime, as say this blue color is your Hurst exponent value of 0.3 and above, so that's representing the combustion noise state. You can see that the multifractal spectrum is broad, wide spectrum you can observe. Whereas for bluff body also, you can see that the blue region, it shows a wide broadband spectrum in the combustion noise. And as you increase your Reynolds number, you will see the Hurst exponent decreases down, and further as you increase the Reynolds number furthermore, you will see that system goes to the state of Hurst exponent very close to zero values. And at this region, you will observe that if you observe the Hurst exponent spectrum, the multifractal spectrum of the system, it collapses to a particular point. From a broad spectrum, the system collapses to a particular spectrum value in a term. As system goes from combustion noise to thermoacoustic instability, there is a loss in multifractality. So from this it is clear that there is a loss in multifractality for this given system, as the system broad spectrum of the system collapses to a particular point as your system transits to thermoacoustic instability. Now said that, so these kind of, so it will be a question like, are these specifically applicable to only a particular type of combustor, or only for combustion systems are they applicable? But it is been shown that this results holds good in both aeroacoustic systems and aeroelastic systems also. In a case of aeroacoustic systems, we can see that when you are at a low Reynolds number values of nearly to 2500 to 3000 values, you will see that system initially remains like this, and this eventually grows and there is a sudden jump to high amplitude oscillations. And so this is a bifurcation plot when you are considering for an aeroacoustic system. And if you plot the Hurst exponent for these time series values, you will see that there is a decrease in Hurst exponent way before the system transits to this kind of oscillations. So if you are getting a warning somewhere very close to the system, far from the system, and you are having sufficient time to do any actions to prevent the system from going to this high thermoacoustic instability. Similarly, if you consider the aeroelastic system, fluttering of the wings, or we try to have a fluttering of the small sheet over here, and when you try to measure this thing, you will see that the amplitude that is on the y-RMS and the velocity being shown over here. Your system initially remains at very low values and it gradually increases to these high amplitude oscillations. Whereas your Hurst exponent values, you can observe that it initially it's above 0.5, showing an anti-persistent behavior, and then it slowly comes down and eventually it decreases before your system actually goes to this kind of high amplitude oscillations. It decreases well before the system transits to this kind of things. And if you see the flutter response and the periodic response of the system, there is a multifractal spectrum for this fluttering when the system is at aperiodic responses, and when it goes to a flutter response where your wings they start to oscillate up and down at a sinusoidal periodic motion, we call that as flutter response, and you can see that the spectrum collapses to a smaller region over here. So the theory of Hurst exponent, where you try to find the different as an early warning signal for predicting this kind of high amplitude oscillations, is quite accurate with different wide variety of systems, and it is been shown by Dr. Induja Pavitran and Professor Sujit that the amplitude of the signal which we have seen here has an inverse power law scaling with the Hurst exponent. This is helpful in some sense. We will discuss how it is helpful. So say in a turbulent flow, and so here they have shown for 5 different systems. So initial what we know is for a bluff body combustor of say length 1400 mm. You can see the circle plots over there, and for a bluff body combustor of length 700 mm. So when you are changing the length of the combustor, your natural frequency changes and your system dynamics also exhibits certain different phenomena. Whereas for an aeroelastic system, if you observe, the green shows the air for an aeroelastic system, and swirl combustor, which is for the annular swirl combustor, if you see, you will see that these orange dots are shown over there. And for an aeroelastic system, aeroacoustic system, and we have seen this dotted line shown here, and we can observe that they all lie very smoothly on a fitted line shown here, and it is shown that this amplitude A, I'll try to write it over here. So this amplitude A over here has an inverse square law power law relation with the Hurst exponent, so h to the power alpha over here, and this alpha value is nothing but 2 has been shown by them. So amplitude is proportional to h to the power minus 2 is shown in this particular paper. So I have cited this paper before. So this universal scaling law has been shown by them, and we see that there is a self-organization in turbulent flows which are leading to this kind of oscillatory instabilities, which follows a universal rule. So different subsystems which are completely different, where you don't have any flame, to a region where you have swirl in the flow, where you have no swirl in the flow, to an aeroelastic system where you have fluttering in the system. So your system is exhibiting this kind of scaling power law behavior, and this slope is nothing but its amplitude inversely proportional to the Hurst exponent square. So this 2 is the slope of this value, which is having a negative minus 2 slope over here. Now once you get a universal law like this, so what is the use of using them in the system, in a given system or anything, is by estimation of the limit cycle amplitude in a class of systems that encounter oscillatory instability. So any kind of oscillate systems that exhibit these kind of oscillatory instabilities, this power law can be used. So how we use it is, say you have different points in the system as this 1, 2, 3 and 4 as shown here. So now in these 4 points, with these 4 points in the combustion noise region, if you are trying to plot these 4 points over here, and if you try with this slope of Hurst power minus 2, if you are plotting an approximate line with these points, so as shown by this dark line, we can see that your system, you can predict the point of where the system eventually goes and contacts this particular amplitude of oscillations. So when your system is at chaotic region, say it was nearly at this region, and as you are moving towards the thermoacoustic instability, using this particular universal scaling, we can predict the amplitude of the, where if you are having data only in this region, I will just erase this. So if you are having, so this, if you are having only the data in the initial combustion noise regime, if you are only having it. Now if you try to use these values and you try to plot a curve through that with the slope of -2, you can interpolate this and you can predict the amplitude of your signal when your Hurst exponent is going further down towards the thermoacoustic instability. So we can predict the amplitude of limit cycle oscillations using this universal scaling law. That's what we have, the people have used, and they have a, Professor Sujit has a patent on this for system identification and determining of the predetermine the onset of impending oscillatory instabilities in practical devices. So they have a software called Ether, where they try to do this live predicting and of oscillations in the system. So it's a patented software where you can use that to predict the high amplitude oscillations in the system with this combustion noise data alone. So that's a significant step towards predicting the things and getting precursors and predicting the amplitude of an oscillation with the stable operation data alone. Once said that, so our aim, people now then try to use the combustion noise data to, before the system goes to this high amplitude oscillations. Using this data, can we do certain things before the system goes to this high amplitude oscillations? Can we do something such that you can prevent the system from going to this kind of high amplitude oscillations, is what people have been doing after this, once it was discovered. So in real world systems, actually the control parameters vary continuously. So this is an important thing. We have rate dependent transitions in most of the systems. In real world systems, we don't actually carry out any quasi steady experiments because your control parameters will be varying in a rate. So if you say this is your control parameter, say V, and say this is your time, sorry, and this is so if you have a time, so this is your time over here, this is your parameter, it's your parameter, not pressure. So this parameter, it changes with time. It can even change linearly, or it can change exponentially over there, or it can change in a particular fashion also. So your control parameter, it can vary in different ways, but it changes continuously with time. Now when the system is changing, when parameters are changing continuously with time, there are different studies which have done this, and it is shown that, say this is the RMS of the pressure fluctuations for a given rate dependent transition data is shown here. So you can see that initially the system remains at, so how they do is, you have the time series, to take windows of them such that you take certain number of windows and you try to plot them over here. Now you can see that initially the system remains at this stable operation and it has very low values of PRMS, and at this dotted line represents the point where the system actually onset of tipping, we say. It's the point actually where the system goes to this kind of high amplitude oscillations. It's the onset of tipping. Okay, so that's not right. So this point is what we call the onset of tipping, and the system goes after that to this kind of high amplitude oscillations. Now here different early warning signals are plotted, and if you observe, the first one is autocorrelation, second one is variance, skewness and kurtosis are the second and third and fourth moment of the system, and H is the Hurst exponent values. You can observe that there is a dotted line which segregates the onset of tipping from the stable operation state to the high amplitude oscillation state. So you can observe that autocorrelation, it initially remains at low values of amplitude, then it slowly gradually increases to a value of 1. So autocorrelation 1 lies between 0 and it's a bounded value, so you can use them as early warning signal. Then comes is the variance of the system. Variance, so here autocorrelation was, as we have discussed, it is the relation between the signal and the lagged value of it. So if you take a lag 1 autocorrelation, you are actually shifting the time by 1, delaying the time by 1 second, and then you are calculating the correlation between the two time series. And that time series, if you observe here, we see that your system slowly it was initially at low values, and you can observe that before the system actually tips to very high amplitude oscillations, your autocorrelation value increases. So this phenomenon of autocorrelation value increasing before the onset of tipping is what we have studied in our nonlinear dynamics called the critical slowing down. This is captured by the autocorrelation value. So how it is captured? We say, because say you had a time series and you are taking a window of it and you are taking the next window of it. Now near to the onset of tipping, what we are, according to critical slowing down thing, we have said is near to the onset of tipping, the any perturbation you give, it will take lot of time for it to decay to a stable state. Now when you are taking the window and you are progressing slowly, you will see that your same time series is being coming into the different windows of the progressing windows. Now when this happens, you will get more and more correlation values between each of the segments. Now when this comes, you will see that your autocorrelation slowly increases from smaller value to higher value, and eventually it goes to, say, when you are having a sinusoidal oscillation, your system eventually goes to this autocorrelation value of 1. Similarly, variance is also a measure P minus P bar, and you take the square of that, and you will see that initially it remains at low values, and so variance is not able to give well before the onset, but it increases at the onset of instability. It slowly grows to this high amplitude oscillations. So it's not much a good early warning measure, you can say. When compared to skewness and kurtosis, you can see that they also show a small trend in increasing, but they also increase at the point of onset of tipping as shown here. So they are also not so evident as early warning signal. Whereas you consider the Hurst exponent values, initially it lies near to 0.3 over here, and then it goes and then it comes down and eventually comes down to lower values before the onset of tipping. So it is able to predict well before the onset of tipping happens, and system, so Hurst exponent and for autocorrelation seems to be a good early warning signal for this particular system of Rayleigh tube which is shown here. Now you need to note here is we are actually considering the rate dependent transition. So the rate here considered is 8 millivolt per second. So by 8 millivolt per second, what we mean is it is the voltage that is supplied to the heater mesh. So now it is changed at a rate of 8 millivolt per second. Now when we do this, and we are seeing that the system transition happens here, and when you increase the rate further, when you increase the rate further to 48 millivolt per second, you can see this your RMS value, instead of jumping at a particular point, is slightly, it moves backward. It slightly moves backward, and however autocorrelation is able to increase well before the onset of tipping happens, whereas variance, it remains very close to the onset of tipping. So this doesn't work. And skewness, it had a gradual increase and then it goes and it settles down to lower values. So it also does not show much as an early warning signal for this given system. And kurtosis, that goes up and it remains down and comes down at the point it's doing all that. So it's also not useful as an early warning signal. Whereas Hurst exponent, if you see, it remained at high values initially, then it slowly goes down to low values of 0 over here. So Hurst exponent is able to show well before the system goes to this kind of high amplitude, low periodic oscillation state. So it is able to show before the system transits to this kind of periodic oscillation state. So Hurst exponent and autocorrelation proves to be a very good measure when even when your system is transitioning at a rate, and further when you are moving at a faster rate of 128 millivolt per second at very fast rates, you will see that your PRMS is having slight increase, whereas your autocorrelation is still able to provide a warning before the system moves to this kind of oscillations, but your variance jumps only near to the onset of tipping. Skewness is now able to show a slight trend in the increasing trend in the system. However, after that point it remains nearly close to the zero. Then kurtosis values, it shows a increase over here and it shows a larger increase over there, and then it comes down to this lower value, but that too happens near to the onset of tipping point. Whereas for Hurst exponent, if you observe, it remains near to this particular point and then eventually it comes down before even the onset of tipping, well before onset of tipping, and so this also proves to be an good early warning signal. So with rate dependent transitions, autocorrelation and Hurst exponent proves to be as a good measure to give a warning of an impending tipping. And now there are different warning times available for different systems. So it's not like we will have warning times as I mentioned for a combustor. If you're considering, the warning time will not remain as same as that is shown there. So now instead we need different strategies for preventing critical transitions, because you need a unified method, but you need to use different strategies for different systems. That is because if you observe here, you can see the warning time that is available for an earthquake is in terms of seconds, whereas for a tornado, tsunami are in minutes, whereas for an volcanic activity or a landslide or an avalanche, you have it in before from minutes to hours to days you can get into. For floods you may get it before certain hours, or in some time in day one or 2 days before you can get the warning. Whereas for social natural hazards like forest fire, you will get warnings within hours, minutes or seconds you may get it. Drought, it will take nearly weeks or months, you will have warning time in between this. Whereas for a nuclear failure, you may have only certain seconds or minutes of warning time available. For a dam failure, you may have minutes or certain number of hours before this kind of catastrophe happens. So there are wide range of warning times available for different systems, but there can be unified methods or standard procedures which can adjust to these kind of different warning time availabilities for different wide variety of systems to tackle different hazards, from natural to socio-natural to technological hazards. We can use this nonlinear dynamics as a tool which can be used to study these very different real world systems. And thermoacoustic systems or combustors are an engineering system which has very high controllability within them. So we can use these controlled experiments to get to know different strategies that are applicable and use it with different, based on your early warning time and system characteristics and all. You can define your different ways to prevent the system or get a warning of a system and do the required disaster management strategies to avoid catastrophic effects in the system. So whatever we have studied using the nonlinear dynamics is helpful not only in aerospace industries currently, but it is useful in different, even for wide variety of systems as I have shown here. Wide variety of systems also this proves to be very useful. Yeah, so that's what I was having for this session on aerospace engineering application of this nonlinear dynamics what we have learned onto the aerospace engineering thing. So I will just try to play this once again so that you now, since we have time over here, we can see how this thermoacoustic instability plot was, how they were able to fix this F1 engine problem. Once you know this, there are oscillations happening, how to fix them, you can just watch it. Yeah, so that's how they solved that issue on combustion instability problems. So the nonlinear dynamics, so current nonlinear dynamics which we have learned through, we can use it to use it as the precursor to the upcoming instability, or you can use them to mitigate the mitigation strategies people have shown, and people have also shown different ways to study the mechanism or the qualitative dynamics which different combustors exhibit, and these are very good examples to study the different bifurcations that are happening within a system, and people have used different ways. So out of that, complex networks method was taught by Shruti over last sessions, and there are many other measures like synchronization and recurrence quantification measures and all, which were key to address these different oscillation states. Now, once said that, for these kind of aerospace engineering applications, we are left out with, I hope the nonlinear dynamics session was helpful for you, and so the applications in nonlinear dynamics concepts in aerospace engineering is completed with this. And so the nonlinear dynamics sessions, so we in this whole session we tried to introduce to the nonlinear dynamics different things which we have seen. So I will just share the screen over here and I will write it down just as a overview of all the things that we have studied. Yeah, so as you can see, so in the introduction of the nonlinear dynamics, we discussed what are dynamical systems. We discussed what are dynamical systems, which we have seen, and we have said that any form of the form x dot is equal to f of x, and if you are having any second order, how to convert them into a first order equations and use them to study the, we have seen the simple oscillator models, simple mass spring systems, and we have explained what are orders and these systems, and what are vector fields for a given system, what are the phase portraits and phase space of the systems, phase portraits for a given system in a phase plane, how you try to do, and we have seen how to find a fixed point for a given system qualitatively when you are having fixed points, and how to say either they are unstable or stable fixed points. Stable or stable fixed points are they? So we are able to see those different fixed points also, and so with that we are able to see what are the unstable and stable fixed points. Then we were discussed about what are the potential functions and how to find those potential functions. Then we discussed what are the linearization methods used to find quantitatively, find quantitatively the stability of a system. So said that, then that was our initial state where we discussed about introduction to nonlinear dynamics. Then we discussed on the nonlinear dynamics state based on bifurcation theory. We discussed next on. So in the bifurcation theory, we discussed initially broad topics on saddle node bifurcation, where we told that there is a sudden emergence of the disappearance or emergence of fixed points in the saddle node bifurcation. Then we talked about transcritical bifurcation. Then we showed about what is called pitchfork bifurcation. So we talked about different examples of all these three different bifurcation setups, and we talked about what is we famously call the logistic equation in this topic, and we talked of how your system evolves and all. Then we talked about laser example where transcritical bifurcation is shown, where system emerges and then suddenly goes to this kind of lasing action. And so we discussed this broadly over there. Then we discussed in terms of flow on circles, so where we discussed about oscillators, where we discussed broadly on two different topics: uniform oscillator, which were of the form theta dot is equal to omega, and we discussed on non-uniform oscillator, where you had theta dot is equal to omega plus at some form, and we showed the example of fireflies, how they synchronize, and how unified flashing of the fireflies happens, and how it can be studied into. We looked into that and said that then we slowly moved into the two-dimensional nonlinear dynamical systems. Here we tried to discuss on the earlier we had x dot is equal to f of x. Now we had introduced x dot y dot is equal to g of x comma y, which are now functions. They can be separate or coupled or decoupled. Now with this set of equations being given, how to find the fixed points. So we came up with new variety of fixed points for these systems. We had saddle nodes. Apart from stable fixed points, we had saddle nodes over there. We had line of fixed points. We had what we called centers. We had called stars or stable nodes. We had something called degenerate nodes. So these were there, and we were talking about all this, and we said that when your derivative f dash of x is approximately equal to 1, you didn't have this proper method of classifying the stability of the system. So for this we said that any small perturbation can bring these borderline cases. So the borderline cases can move from one stable condition to another. And if you remember, we had used a simple way of classifying these borderline cases like this, and this was delta and this was the trace of the system, and we saw how to find the Jacobian of a matrix and use it to find the trace and determinant, using which we were able to explain the details of the stability of the system. Now said that in the 2D bifurcations, and once that was spoken to, then we saw different examples of this saddle node bifurcation and different things in a two-dimensional way, how it can be used into, and we were seeing different examples in which we saw one thing known as Lotka-Volterra model, which used the population of rabbits and sheep we discussed. In which we saw how in this case we discussed broadly on this topic called basin of attraction, and we talked something called basin boundary, and we were able to say how if you are starting at a basin boundary of system, which is your stable basin boundary, and which was your borderline case, which you are able to bring if you are starting at which point where you will be eventually moving on to. So these all things which we are able to say there. Then said that then we moved on to something called limit cycle oscillations. So in the limit cycle oscillations, we said that we have a closed orbit normal closed orbits we had, which are not called limit cycle oscillations. For closed orbits, you will have more number of closed orbits around it, whereas if you have an isolated closed orbit, we mentioned it as isolated closed orbit. When you have, we mentioned them as the limit cycle oscillations. And today in the applications, we saw how your system transits from a chaos via intermittency to thermoacoustic instability. And thermoacoustic instability signal, if you see and plot it, you will see that the system exhibits a limit cycle oscillations. And once for this kind of limit cycle oscillations you will see, we saw different kind of bifurcations for this kind of 2D systems, where we saw similar bifurcations for saddle node bifurcation, transcritical and transcritical, and pitchfork bifurcations were similarly seen for 2D also, or two-dimensional bifurcations also we saw. Apart from that, when we are discussing about limit cycle oscillations, we were discussing about ruling out of closed orbits, and in that we discussed about gradient systems. If you are able to say your system is a gradient system, you were able to say your system will not have a closed orbit. Then if you had a Lyapunov function which represents an energy like thing, if it is able to present there, then you ruled out presence of a closed orbit. Then you had something called Dulux criteria to rule out the closed orbits. Then we discussed on how to say that there are closed orbits. Closed orbits are present, or confirmation we wanted to do. For that, we had this what you called Lennard's theorem, or Lennard's theorem we had to say if your system had, and after, during which we discussed about a famous this called Poincare-Bendixson theorem, in which we discussed the why in 2D you will not in 2D you will not observe chaos. Then we had a tutorial on application of this linear stability analysis and oscillations, where we tried to use MATLAB codes to perform the different plots and bifurcation related things. Plotting we learned, and then we slowly entered into the topic called chaos theory, where we initially introduced you to the term called of Lorentz equations, which we introduced you. So using this Lorentz equation, we discussed a famous example of chaotic water wheel, and we showed you the video of chaotic water wheel experiments, how it is moving, how it produced these different oscillations, and we showed how these systems are dissipative in nature. The systems are dissipative in nature, and we showed how your volume decreases as your system evolves. Then in chaos, we were able to, once we saw these things, then we discussed about something called Poincare map, or then we discussed about something called Poincare section. So when you had a oscillations, and if you had a section being given to that, we saw that we can plot the Poincare section, and we can determine the state of the system using point resection. How is it a periodic or a chaotic system? A state is it's chaotic or periodic, you can observe from the Poincare sections. And with those Poincare maps, we were discussing about Lorentz equations and Lorentz different criteria we were seeing. We tried to, then we saw how Lorentz explained his criteria, his chaotic behavior. So if you remember, we had a plot somewhat like this, then it went like this. So this Lorentz was able to explain it using the Lorentz map, where he had the time series, where he took the Zn and Zn plus 1th peaks of them, and then he plotted it, which lied on a simple curve. So he got a order from chaos as by plotting this map. Then he was able to explain different things over there. Then once Lorentz map was studied, then we slowly moved on to what we called 1D maps. So in 1D maps we discussed what are iterated maps we saw, which talked about discrete time evolution. We saw the different examples of the discrete maps where they could be applied, and we were talking of, in these maps we were talking now majorly on the called logistic map. And so logistic map, as we discussed how its correlation with the xn plus 1 or xn into 1 minus xn term came, and xnth generation and xn plus 1th generation, how you can use it. Using this, as in the middle we were just mentioned about how the Poincare map and Lorentz map are different from each other. Then the logistic map, once we said, then we moved the R from different values. So when we moved R at different values, then we saw oscillations damping down, oscillations moving in period 2 cycle, then oscillations moving in period 4 cycle. Eventually we saw what we called period doubling route to chaos, which we saw. And in that we discussed that in between you had something called period 3 windows within these systems, and in order to discover them we saw that you need to have 2 points for period, for a 2 solution point, and in order when you combine them you will see that you need to have a square of that to see the thing. And in order to plot that, you had a curve and you tried to plot it with these two different things, and you observed why there is a period 3 window being observed in the system. And famously logistic map, when we were drawing, we saw that it had a curve like this. Sorry, just erase this region. So it had a map like this, and we observed with a rate less than 1 it was like this. At r equal to 1 it became tangential to the surface, and above that it became crossed and it became like this. Sorry. Yeah, so for r greater than 1 this moved and it moved like this. So it had an intersection point, and we discussed something called cobweb diagrams to learn these different things very easily. And we saw how if you have a 45-degree line, and we talked about the importance of this 45-degree line also. 45-degree line where f of x star is equal to x star conditions are met. Then we saw how a cobweb diagram needs to be made. If you had a curve like this, you jump over here, then you move, then you move to the next line, then you move over like this. So if you start from here, so you saw how there can be oscillations, system moving to particular state, or the Y system meant to this carrying capacity after a particular point. We saw that in the system also, and using the cobweb diagram we were able to show that in the logistic map. Then we moved on to a topic called fractals, where we said fractals are nothing but fractional dimensions they have, which has self similarity over different scales. Self similarity over different scales. Then we talked about what we called Cantor set, a standard fractal set where we divided it into 3 parts. Then we had something called Koch curve, von Koch curve we mentioned, where you had a curve, we made it into 4, then further you made it into further down, so that's how we were able to see. And using this one Koch curve and this, we were able to show how their dimensions were. D is related to del of m by del of n, how you different Cantor set got a fractional dimension of 0.62, one Koch of 1.29, how it was able to get. We were able to show that. Then we talked about box dimension. If you had a curve number of boxes that of small epsa that can fulfill your required things, we are able to show, and we showed that number is proportional to area, and so D was calculated, box dimension was calculated according to that. And then we discussed on box dimension, then we calculated pointwise or just called piecewise dimension. So in this piecewise dimension we are able to show how a correlation dimension and piecewise dimension are cumulative dimension when you are taking by what way is the difference between this piecewise and cumulative dimension, and how these each different dimensions they were able to get to the values of these things. So that was about correlation and piecewise dimension which we discussed. Then we discussed in the tutorial 2, we were discussing about different engineering and physics applications. There we discussed about early warning signals. What are the different early warning signals, how they are used in different areas of climate, paleoclimatic data, then in building management systems, then how they are used in a turbulent reactive systems, and we were able to show how these early warning signals can be used to predict an upcoming transition. So we were able to show that, and in MATLAB we were able to show how to calculate this logistic map, Lorentz equation, how to plot and get the different phase-based trajectories and different axis values, and plot the Lorentz curve and all, logistic map, Lorentz equations. Then we talked about how to cut the Poincare section, get the Poincare map over that. So we are able to show those things. Then today we talked about application specifically related to aerospace engineering. So when we are talking about application related to aerospace, we showed how in engineering what we called combustion instability was a plaguing problem in how in industry, how it is a plaguing problem, and how this problem was tackled using nonlinear dynamics tools. Dynamics used to understand the dynamics in a particular system. And we saw different turbulent systems, and we saw the difference between combustion noise, that is a practical experimental result. We saw how it is chaotic time series, and we saw for thermoacoustic instability how it's the periodic signal or limit cycle signal, how it behaves. And we saw an intermediate state between them called the intermittency, through which the system transits from combustion noise to thermoacoustic instability. So this intermittency now presages this thermoacoustic instability and acts as a early warning signal. Once we got this early warning signal, we wanted to see qualitatively how this happens, and for a system like Rike tube which we showed, we saw how we got both supercritical and subcritical, how we got both supercritical and subcritical half bifurcations for this system, and we showed the variation of Hurst exponent for each cases, and showed that actually loss of multifractality happens in the system as we move from combustion noise to thermoacoustic instability. Said that when we discussed how the different early warning signals behaved for different rate dependent experiments. And we saw that autocollision and Hurst exponent were pretty good early warning signals for the combustors shown. And using this all, we were able to explain. So finally we showed the collapse of multifractal spectrum thermoacoustic instability. So that was key inferences from them, and finally our aim was to see the application of nonlinear dynamics into the aerospace industry, and at the end we showed this is not limited to aerospace engineering. We can use these tools for a wide variety of real world systems and hazards with different warning times. These systems which are not capable to do rigorous experiments the engineering system results can be used in the benefit of much wider real world systems. Benefit of much wider real world system problems. Our analysis. So basically I hope the nonlinear dynamics which we have used was helpful for our understanding in I hope at least a bare minimum understanding we were able to get basic understanding of what nonlinear dynamics is, how to use them, how to approach this nonlinear behavior in these systems. In a system, if you are having a dynamical system equation, how to use it and all. Now, so by tomorrow we will have the last session in this series, where I will try to talk about systems which, if you are not able to have a dynamical system equation, then how can you tackle these problems on solving them to how we can study such systems where you have a wide variety of data, very high dimensional data with you, but then if you are not able to write a dynamical equation for that given system, how can you use it to how can you study those kind of systems which have very high dimensional data. So in order to do that, we will be checking into what we call as Koopman operator details and all. So that we will discuss in the next session, and so that will be our final session. So if you have any queries or any doubts related to any of the sessions, you can just put a message to me. We can discuss over that. And yeah, so I hope we will complete the series by tomorrow. If any questions or any of these things are there, we can discuss over that. So I hope this nonlinear dynamics series was helpful for you. To at least to some extent it was helpful for you to understand the basics and understand the subject, how it can be used. So it can be helpful in different ways. So people are now rigorously using these tools to unravel a lot of inbuilt dynamics shown by the systems and explain how it is happening and all. So I hope this was a helpful in for yours for your career. So I will stop for this session today. Yeah, thank you very much.